has two. So you have two kinds of edges. So you have directed and bidirected edges. So I'll explain what this means in just a bit. So to take an example, let's say you have a graph that looks something like this. So you could have 4 vertices, and then you have some form of edges between them. So you have a directed edge. Here you have edge between A to B, B to C, C to D, and you have some form of bidirected edges. So what this represents is as follows. So you have random variables corresponding to each of these vertices. So let's say you have 4 random variables, xa, xb, xc, xd, and these random variables are their relationship is determined as follows. So you have xb is some variable lambda ab times xa plus some noise variable which is corresponding to this vertex. Likewise, xc is lambda bc times xb plus some noise, and xd is some variable xc plus noise here, and the variable xa is just the noise eta a. And then we make the following assumption. So the assumptions are that this vector eta, which is so this is a standard normal. So this is a Gaussian variable. So meaning this is coming from some normal variable with 0 mean. Its covariance is omega, which is unknown. So likewise here in these equations here, this vector or this matrix lambda, which is this is a 4 cross 4 matrix, and then most of it is 0 except lambda AB, lambda BC, and lambda CD. The rest of those zeros. So the model is such that this graph. So this graph here determines the zero. So the directed edges of the graph determine which entries in lambda should be 0. And the bidirected edges determine which entries in omega should be 0. So more specifically, if there is no if there is.
I think so. So is it omega or omega inverse?
It determines it in omega itself, not omega inverse.
I see. But isn't it usually in graphical models, Gaussian graphical models, usually people look at the precision matrix, right? Not the covariance.
Yeah. So I think so. Like throughout this this line of literature, I think the assumption is this graph determines omega. I think like these are just like a notational convenience, right? So I think if you assume 0 pattern in omega inverse, you'll get just a different kind of graph. So in particular, I think given this graph, you get some 0 pattern either in omega or omega inverse. So for this talk, we'll talk about 0 pattern in omega.
And so the second question that so this notion is related to chain graphs.
So, sorry, what is a chain graph?
So chain graph. You also learned about chain graphs recently, but basically they are another kind of graphical model which is mixed. So they have directed and undirected edges. And
right.
So it's also quite similar. They also. I guess there it's omega inverse instead of omega. But there are multiple different interpretations right. So basically, again, the directed edges are given by your lambda, and the undirected edges correspond to the precision matrix or the covariance matrix of the Gaussian. I was just wondering. Is that another name or is it? You haven't seen it.
So I think so here the interpretation is that these things just tell whether this noise is correlated or not in some sense.
Okay.
So it's yeah.
Okay.
Uh,
Anyway, sorry for interrupting. So usually we
yeah.
encourage people to talk. Is that okay?
Yeah, this is perfectly fine. Yeah, I think I prepared in a way such that this is like fairly interactive. So
Okay. Okay. Great. Thank you.
yeah. So yeah, so like for this talk, we'll assume that this graph tells us what should be the zero pattern in lambda and what should be the zero pattern in omega. So in particular here, so we see that there's no bidirected edge between A and B. So omega of AB should be 0 and omega of BA should be 0. So in particular, if there is no bidirected slash directed edge, then the corresponding values in omega slash lambda should be 0. Okay, so and then like the one of the problems in kind of causal inference and in particular LSEMs is the following, that the problem is so you're usually given this graph, so given this bidirected graph, so you can think a mixed graph. So you can think of this as to be a model. So you're given a model of the world, uh, which is an assumption you can make, or you get it from domain knowledge or somewhere, but you have this model you're dealing with, and the random variables. So you're given these two, and you want to ask, can we obtain this matrices lambda and omega uniquely? Right. So this is the identifiability problem. So this is like a one of the common problems you can ask. So that is you have a graph and you see these random variables x. In practice, you either measure it from finite samples or you get it in some form or fashion, and then you want to ask how do I retrieve these matrices lambda and omega. So here, going back to this graph, what this graph means is that it's kind of encoding some form of causal relationship. So it's saying, okay, like A is causally related to causally affects B. What is the strength of causality? So that is given by this matrix lambda, and this omega is just the correlation matrix of the noise. So this is the problem we want to study. So more particularly, you wouldn't. Since you assume that you have like enough samples, so you assume instead you have both the mixed graph and you have this matrix sigma, which is just the expected value of x transpose. So essentially, you assume that you just are given the covariance matrix, and then you want to retrieve lambda and omega. So note that since the way we've defined this entire system, each of these x is also a Gaussian random variable, and therefore with mean 0. So therefore, like these two questions are just equivalent. And so we want to ask, when can we retrieve this uniquely? So this is the problem of identifiability. So are there any questions at this point? Okay, so sorry, was there a question?
A quick question. So, for the omega, actually, what would be a good kind of case or example for that? The correlated
Sorry.
noise. What would be a good example for correlated noise over random variables?
What would be an example of correlated noise over random variables?
Yes.
So you could think of something like, let's say, let's take maybe the simplest example, I guess, of I mean, let's say you have some form of smoking and you have some form of some variable for cancer, and then a correlated noise between these two could be something like, I don't know, predisposition to smoking and cancer. So some genetic predisposition. So that could be one form of correlated noise. Or a much more simpler and a realistic example could be that, let's say you're measuring two variables and you're using the same instrument, right? So the instrument that you're using to measure both of this will have some form of error, and that error is correlated, for instance, or things like that.
Right.
So that's like a example of why there would be correlated noise.
Okay.
Okay, so then I'll go about describing this algorithm very briefly. This is due to, I guess, Foygel. Let's okay, so this they characterize when you can essentially retrieve this pair lambda omega from sigma uniquely. And then one of the condition is one of the sufficient conditions is what is called the Bow-free assumption. So it's the Bow-free assumption. So which is that it just says that you cannot, if the mixed graph doesn't have both bidirected and directed edge between a pair of vertices, then it's uniquely identifiable. So essentially this condition where you don't have both the bidirected and directed edge between a pair of vertices is called Bow-free assumption. And their main claim is that if you have such graphs, then these are uniquely identifiable. So I've been making some, I've been being a bit imprecise. So when in the identifiability problem, you kind of, you wanted to hold it. So there's maybe an aside. So there's a distinction between identifiability versus what is called generic identifiability. So this just means that you want to, here we'll be looking at generic identifiability in the sense that you don't want it to hold for all pairs. So this algorithm should work for almost all pairs. Should work for almost all sigma for a given graph. In particular, like the only failure cases should be a probability zero event. So this is just an aside. So this is just to make sure that there are no these. You can imagine a case where like if you sample a random sigma with probability zero, there will be these edge cases which you cannot handle. So you don't want to deal with such things. But for today, we'll just not go into this, and I'll be using identifiability versus generic identifiability like interchangeably. So this is just an aside. Okay. So
I have a quick question.
Yeah.
So for this problem, you don't assume any interventions, right?
Yeah. So there is no notion of intervention here. So this is just like a purely statistical question at this point. That you're given these samples, there's no more interventions. How do you retrieve these parameters? So the way is that like so essentially you can think of it as you've concluded your experiments. You cannot collect any more data. So purely from this observational data, can you retrieve your parameters? Okay, so let's see what this algorithm is. So this algorithm is kind of fairly natural, right? So let me instantiate it on a specific kind of graphs, and the reason I'll instantiate it on this is because that's the kind of graph we are going to look at for this talk anyways. So these are what I'll call these as paths, like, or bow-free paths. So these kind of graphs are just what it says. So it's just that it's a path. So meaning your random variables can all be lined up in an order of a path. So something like this. So here's a simple example on 4 vertices, and then you since they're bow-free, you can assume that there won't be bidirected edges whenever there's a directed edge, but there could potentially be bidirected edges between the other pairs of vertices. See this and this. Okay, and what the Foygel et al. Algorithm does is the following. So essentially, it solves for this set of equations. So let's go back to the model, right? So the model was that your xi is some lambda parent of I comma I times x parent of I plus some noise at I. So you can group up all these set of equations and write this as the following matrix notation, right? So this is x equal to lambda transpose x plus this vector eta. If you rearrange this and so if you do some rearranging, you will get I minus lambda transpose x is eta. This is equivalent to the following notation, that omega equal to I minus lambda transpose sigma I minus lambda. Right, so you can just take you can just multiply this equation with x transpose and take expectation, and you get this. Right. So then, and then given the graph determines the zero patterns. So it determines the zero patterns in omega. And then essentially what this algorithm does is solves for the set of equations that at the zeros of omega. So you just set up that set of equations, and then you solve for these equations wherever this equation here evaluates to 0, and that you get that looking at the graph which you're given as input. Right. So how do we do this? So the problem here is that all of these lambdas are unknown, but given this bow-free nature, and for instance here it's a path, you can kind of solve it in a iterative fashion. So you can, or inductive fashion. So first you can solve for lambda 1, 2. Then you use the computed value of lambda 1, 2 to solve lambda 2, 3. And you use the computed value of lambda 2, 3 to solve lambda 3, 4, and so on. So in particular, it just turns out to be a set of equations. I'll just like write down what it finally looks like, but it's easy to work this out. So essentially what it turns out to be is that for so the first pair, lambda 1, 2, just turns out to be it's sigma 1, 2 by sigma 1, 1. And then from there on, for say I greater than or equal to 2, it turns out to be lambda parent of I, or I greater than or equal to 1 here. Sorry, parent of I comma I, you have, it turns out to be that it's just say lambda. Okay, so for simplicity, I'll just call these vertices to be like of the order 1, 2, 3, and so on. So I don't have to keep writing parent of I. So then let's just call this here. So let's say I minus 1 I would be I minus 2 I minus 1 times, actually let's just do this. So would be of the form So it would be of the form I minus 1, I minus 2. It would be then sigma I minus 1, I plus 1 plus this. So it'll essentially be a division of two polynomials. So in this case, it's just going to be a polynomial of degree 1 times. So you can see that when you can compute this inductively. So you would first compute for the first edge weight here, lambda 1, 2. Then you would use that to compute lambda 2, 3, and so on. And the key idea is essentially this, that you look at this equation here, and then you just look at its zero patterns, and then you just solve for the set of equations. So this is pretty much the algorithm they give. And the claim is that whenever it's Beaufry, you can always solve this in such an inductive fashion. So I instantiated it specifically for paths because that is the simplest case you can think of, but it kind of works for more general graphs as well.
So it's I minus 2, I minus 1, and the lambda.
Yes. Sorry, I think this should be
the numerator lambda, I think.
Yeah, I think I got the signs wrong. This should be I minus 1 I. Yeah. Right. So both of them should only depend on just the previous computation.
Right. Okay.
Yeah, and also surprisingly, like it doesn't depend on like to compute lambda I plus 1, it just depends on like 4 different coordinates in sigma around II. So that's going to be critical as well for the future results we're going to see.
And this works even if you have a tree or something like that. I mean, if it's not a path.
Yeah, so if it's a tree, you can still compute it. So it's going to be slightly different, but you can use this algorithm to compute for a tree as well. So as long as I think there's an ordering, so it's even more general, like the graphs can have directed cycles, but as long as there are no directed cycles and it's Beaufry, you can use this algorithm. And
is there a general characterization of for which graphs it's identifiable?
Yeah, so the general characterization is what is called Beaufry. So as long as
it's not just for paths, but for any graphs.
Yeah, for any graphs, as long as you don't have both directed and bidirected edges, you can use this algorithm.
And whenever it's Beaufry, this algorithm works.
Yeah, so it works generically in the sense that whenever it's Beaufry, for almost all parameters of sigma, it works. Yeah. So in fact, like this is not like the state of the art in identifiability. So like there are like subsequent works which show that even for graphs that are not Beaufry, but they hold certain other sufficient conditions, you can do generic identifiability. So yeah, that's a good point. Maybe let me write it. So subsequent works show that extend Beaufryness for generic identifiability. But it's still like an open problem as to like what is a necessary and sufficient condition. It's still open.
Sorry to interrupt again. I mean, so what you mean is that there are Beaufry graphs which are generically identifiable. I mean, there are graphs which have bows, but they are generically identifiable.
Yeah, exactly. There are graphs which are non-Beaufry, but they are generically identifiable. And in fact, like it's not even, so the exact characterization is still open, meaning that like what are the set of graphs for which you know generic identifiability, and if that condition doesn't hold, there is no generic identifiability. So that problem is still open. So unlike, I think there's another model called Markovian or semi-Markovian model where this answer is exactly known, but for linear LSEMs and this form of generic identifiability, it's still an open problem, both the necessary and sufficient condition. So yeah, so are there any questions at this so far? Okay,
So I
Sorry.
have one question. So you mentioned about semi-Markovian, then it is known completely characterized?
Yeah. So, I mean, one form of identifiability model for semi-Markovian graphs are like kind of completely characterized, meaning that you know exactly on which graphs it is identifiable. And if the graph doesn't hold such a structure, you know that it is not identifiable. So for instance, in LSEMs, it's not clear that even these subsequent characterizations, if the graph doesn't hold such a property, is it always not generically identifiable? So all of these are just a bunch of sufficient conditions, and each one is a slightly weaker condition than the prior work.
So what is semi-Markovian here in this setting?
So the semi-Markovian is like a completely different kind of models.
Okay.
Yeah, so, I mean, I think there was just a passing comment that there are other models of causal inference where such things are exactly known. Yeah.
All right. Thank you.
Yeah. All right. So so far this is about prior work. So what we ask is the following question: that so here one of the assumptions you make is that you know the data exactly, meaning you know this matrix sigma precisely. So, but in the way I motivated this particular setting is that you conduct an experiment and you get finite samples. So you get finite samples of X and you construct your sigma from these finite samples. And then we are asking, and then you usually run such an algorithm, say Foygel et al. Or equivalent algorithms. Then the question is that does this algorithm still perform correctly? So this is a pretty vague question. So what I mean is the following. So the more precisely, this is what I'm asking. So let's say you have instead of computing sigma, you have some sigma hat, which is close to sigma. And then if you run this algorithm, if you run the Foygel et al. Algorithm.
So I just have one more question. Can you clarify what is sigma? I just little confused.
Sorry.
What is
so sigma is essentially the covariance matrix of your data. So your data is X. X is essentially the random variable corresponding to each of these nodes, and sigma is just its covariance matrix. So sigma is just expected value of XX transpose.
Okay, thank you.
So yeah, if you go back to these set of equations, you can see that X is also a Gaussian variable with mean 0. So knowing data is equivalent to knowing this covariance matrix sigma. Yeah, so the question we want to ask is, instead of computing this, computing your parameters using sigma, if you use matrix sigma hat, which is close to sigma, I'll define what close means. And then if you run Foygel et al. Algorithm, you will get parameters, let's say lambda hat and omega hat. How close / far is this pair lambda hat from the true parameter you would have retrieved if you used omega. So this is if you using sigma. If this is computed using exact sigma. So essentially, this is the problem of robustness we are asking. So instead of if you use the algorithm on a slightly perturbed matrix instead of the actual matrix, are you going to get parameters that are close to the original one or extremely far from the actual computation?
Yeah, just one question. I mean, we were wondering about this problem in another context. So suppose you don't have any bidirected edges, right? So suppose you just have a like a linear structural equation models without any hidden variables. So then, like, what is the? I mean, else known about this question?
Even so, that's a good point. So even then, kind of, as far as we know, there's not much known about it. So even if there are no bidirected edges, so the simplest setting where you know a lot of things is just one bidirected edge, or one directed edge, which is essentially solving linear set of equations. So
Right.
there you know precisely like how robust, like how much noise you can add, etc. But once you start composing these linear equations, as far as we know, there's not much known. Yeah, so but that brings me to this point, that so the simplest version of this question is you exactly have one set of so you just have one edge in the path example, or you have something where you have your depth of the graph is 2 or 1. So the simplest setting is let me call it, I guess, yeah, or depth of the directed graph is 1 and no bidirected edges. So this, then the Foygel et al. Algorithm just reduces to solving linear equations, solving one set of linear equations. And that is, and their robustness and, in this particular context is known. So their robustness is well understood. So in some sense, we are just asking a slightly extended version of this form, that if you keep repeatedly solving linear equations and you're using the output of one linear equation as an input to the next one, how does robustness look like? So let me formalize this thing even more precisely. So let's formalize robustness. So to formalize this, we're going to use this metric called condition number. So this is kind of a standard like concept you use in numerical algorithms. So condition number is defined as follows. So you can think of this problem as a map from. So you're computing the map. So you're computing the map sigma to this. Okay, and so there's a if you go back to this original set of equations, right? Okay, I'll just rewrite it. So the original set of equation was that you can write omega as I minus lambda transpose sigma I minus lambda. So in some sense, if you compute the map, if you compute the value sigma, you can retrieve omega in a robust manner, since you're just going to be doing multiplications and not taking any inverses. So we're going to rewrite this as you're just interested in the map given sigma, compute lambda. So we're going to be interested in this particular map. And then the condition number is going to be defined as follows. So the condition number is, we'll use a parameter, say gamma. So let me write it and define the term. So we're going to call relative distance between lambda hat and lambda divided by relative distance between sigma hat and sigma. So this is essentially the condition number. Okay, so now here there are a bunch of terms I need to define. So what is relative distance? So relative distance between two matrices, A and B, is defined as, so look at all pairs, so look at each of the entries in A and B, and then look at this particular value, or the way I've written, let's go. And so just take the max overall, Bij not equal to 0. So essentially, in some sense, it's the maximum coordinate-wise distance between the two matrices, and we'll just normalize it by the value, so that it's if you increase both the matrices by some scalar, this relative distance shouldn't increase. And then the condition number essentially is the relative distance in the retrieved parameters to the relative distance in the your input. So there's just relative distance in output to relative distance in input. That's the right way to put it. And I'm not really told how far is sigma from sigma hat. So in particular, we're going to make it a bit more formal. So sigma hat is obtained from sigma as follows. So sigma hat is essentially, you take sigma and you add an additive noise, let's call it epsilon, where epsilon is so epsilon. So at each coordinate, you perturb it by a very tiny value, which is, let's say, gamma times sigma ij. So each of the coordinate is multiplied by this value gamma times sigma ij, and then the condition number which we define formally, which takes as input sigma and gamma, is defined to be in the limit when gamma tends to 0, which is as the noise becomes closer and closer to 0, what is the value of this quantity? So relative distance of, let me parameterize this by gamma here. So essentially we're asking, as the noise becomes closer and closer to 0, how does this value change here? So does this value...
Question. So
yeah.
Why do you formulate it in this way? I mean, like, wouldn't it make more sense to think about it in terms of sample error? Like, you make a finite number of samples. So then it's not arbitrary perturbations to the covariance matrix, but really, perturbations which come from sample error.
Yeah, that's a good point. So if you assume that, so sample error is only one of the kinds of errors. So here, like, we want to capture all kinds of errors. So the other kind of errors could be like systematic measurement errors. So which is why we are interested in like the worst case errors. So, but you're right that like if you just focus our attention to just say sample errors, we'll probably be able to get much stronger results than what we end up getting assuming adversarial errors. But the motivation behind that is because we want to capture all kinds of errors, and we want to capture numerical errors, systematic errors, and of course sample complexity errors. So which is why we look at the worst case bounds. But it's a good point that like probably the most important or the most canonical kind of error would be the finite sample error, which would probably help us get better results. So this is the notion, this is the measure of complexity we would use. And this is like a fairly standard metric in like numerical algorithm. And to get an intuition of what should this quantity look like. So if this quantity kappa, if this quantity kappa is something like a polynomial in the number of vertices, then it's considered to be well conditioned / good. So this is the good case for us. If it is, say, exponential, unbounded, etc., then it's bad. So then the question becomes, the more formal question of what robustness is that when is this condition number kappa, when is this polynomially bounded? So here polynomial is in the number of vertices. And essentially like in the series of papers, or like the two papers we have, we're just studying this particular object. And we're seeing when does it work well and when does it not work well. And what are some sufficient conditions we can get to show that this is polynomially bounded. So, but before I proceed, I'll ask, are there more questions? Okay, so if not, so I'll probably tell the main results, but maybe I won't have time to explain like the proofs of these things. But I think proofs are not as important as the main conditions themselves. So the first question you may ever ask is the following, right? Question one is it ever bad? Like, I mean, it may be that this is just a simple problem, like it's always polynomially bounded, so there's never a bad scenario. So like the simplest answer is that both the notion of condition number and the model itself generalizes linear equation, like linear systems of equation. And we know that there are bad examples when, and there are ill-conditioned examples. So in that sense that you cannot hope to have that there are no bad examples for LSEMs itself. But a more concrete answer is, I'll give a simple example, which you can work it out later to see that it's actually ill-conditioned. And also there are simple simulations I can show where this condition number grows exponentially. So the example is as follows. So consider the following graph, right? So it's again on 4 vertices. And then between every pair of vertices, we have a bidirected edge. Meaning every pair of vertices where there's no directed edge, we have a bidirected edge. So which will end up being these 3 vertices. And the omega you can define it as follows. So you have so epsilon, some parameter which you can control to get arbitrarily bad condition number. So the first thing you can verify is that this is positive definite. So this is a valid covariance matrix. And then this lambda, which we'll consider is just this half. Okay. And then if you try to compute sigma, so you can compute sigma from this formula, which I just wrote before, which is yeah. So if you compute sigma from this formula, you get a particular matrix of sigma, which I'll just write it for the sake of. So the sigma looks something like this, which is so you get. So you can verify that this computation is indeed correct. So this is epsilon, which we will use to so essentially this shows that there is some okay, so this is the sigma you get corresponding to this lambda and this omega. And then we'll now add, do sigma hat, which would be, as I just described, sigma plus this epsilon, where epsilon ij is exactly equal to gamma times sigma ij. So on each of these coordinates, you can do this additive error. So since there are no zeros in sigma, all entries will be perturbed. And then you can show that the relative error between sigma hat and sigma for this example will be something like 4 times gamma, right? And the relative error in lambda turns out to be, so if you compute lambda hat from the sigma hat, the relative error turns out to be 1. And then, let me see if I got it right.
Sorry, I'm a little confused. Why is it 4 gamma? Why isn't it exactly gamma? I thought, because it's sigma hat minus sigma divided by sigma, right? So it's only like epsilon.
Oh, sorry. Yeah, you're right. So this is exactly gamma. And yeah, so let me write this expression for this a bit more carefully. So what we end up getting is on the max coordinate, you end up getting this relative distance to be something like, okay, sorry, I don't have this expression computed now. So what you ended up getting is that as epsilon goes to 0, this relative error between lambda hat and lambda goes to 1. And therefore you can notice that the condition number is something like 1 over gamma, which is, and when as gamma goes to 0, this is unbounded. So this is like a simple one example, but you may ask, is this the example that is, for instance, of probability 0? That is, that do such examples happen often, or is it just one, like a corner case? So it turns out that it is not a corner case. It's, let me see if I can switch to the, so are you able to see my PDF?
Yes.
Hello. Yeah. So this is a simple simulation I have here. So the x-axis is the number of vertices, and the y-axis is the log of the condition number I described here. And then I'm just generating random instances. So I'm generating lambda to be a uniform. So it's still a path. And then each lambda ij is just a uniform random variable between -1.2 and 1.2. And omega is a random PSD matrix which satisfies the 0 patterns. So I wouldn't go into details on how to generate it, but you can generate it using like the gram matrix. So now on this instance, I compute sigma, and then I do the same thing. I perturb sigma slightly, and then compute lambda hat and omega hat, and then compute the condition number. So as you can see that even the log of the condition number kind of grows linearly or polynomially. This implies that the condition number is growing exponentially. So basically, even on random instances, as long as this lambda is large enough, you can see that the condition number would be pretty bad. Or in our setting, bad implies that it is not polynomial. So therefore, this is not a trivial problem. So having convinced you with that, let me proceed. Yeah. So having convinced you with that, so then the conclusion here is that there are many bad examples. There are many ill-conditioned examples. Okay, so then the main result of the paper is essentially, or one of the main results is that when conditions below hold, the let me call it when properties below hold, then the condition number is bounded by O of n square. So essentially, we identify certain sufficient conditions and show that under these sufficient conditions, this particular algorithm, Foygel et al.'s algorithm, is actually well conditioned. And what exactly are these sufficient conditions? So the sufficient condition is, so the properties slash sufficient condition is, so the first condition is that each entry of lambda ij should be at most 1. So as I showed in the example, the way I had to construct bad examples was when this lambda ij values were larger than 1. And the second condition is something like diagonal dominance. So in particular, you want each of these variables so each of these should be true. That is that. For some alpha strict less than 1. So as long as these four conditions hold, the condition number is at most O of n square. So let me interpret both these conditions a bit more. So this condition, you can think of it to be like a normalized form. So you can imagine that if this value is larger than 1, so let's say it's a large value, like something like say 100, right? So the error you will accumulate in the first round of computation would get magnified, and it would get magnified by the so anything for any value larger than 1, these errors will compound. On the other hand, if these values are less than 1, even though there's an error in the first round of computation, the value you will use to use the first round of computation will not get magnified. So that's like the intuition behind why you need something like this. So in fact, like from most of our random instances, this seems to be the only condition that you actually need. This condition we just need purely because we are assuming adversarial noise. So this is, for instance, if you assume that we are only dealing with sample complexity, our intuition is that most likely you don't need this. But to tie it back to the simplest form, which is the solving linear equations, one of the first known sufficient conditions is exactly was for diagonally dominant matrices. So in that sense, this is kind of similar in spirit to linear equations. Of course, this is not directly comparable to diagonally dominant matrices, because there the diagonal should be larger than the sum of all other coordinates. But here we are just assuming that the diagonal should be larger than some fraction of one of the absolute values. So they're not directly comparable, but in spirit they are comparable. And I'll just say one last thing before I take questions. So the other thing we also show is that these are not some kind of these are not some kind of very small set of conditions. So in particular for random matrices, I've not defined what the random process is, but for some very natural random matrices, lambda and omega, these properties hold with high probability. So essentially, this kind of says that like there are large enough set of instances where such properties hold. Yeah, given the time, I'll just stop here and ask other questions. So is the sufficient condition clear? So, or the main result clear? So essentially what we're saying is when these conditions hold, the condition number is going to be small. And the small here is polynomial in the number of vertices.
Yeah, great. Yeah, thanks for the talk, Karthik. So I just have a question. So
right.
the last, I mean, I guess the random matrix process, which the last bullet is different from
right.
the figure, right? So in the figure, you showed that most.
Yeah, it's different from the figure. So this is like we proved theoretically that like if you have some form of random matrices, so these random matrices should of course satisfy this property. So the figure I showed actually violated this property. So so this we here the random matrices satisfy this property, and then we show that such matrices satisfy this property with high probability, and therefore such instances are well conditioned.
And my other question is, what does alpha determine? I mean, alpha kind of goes into the condition number.
Yeah, so alpha kind of is, you can think of alpha to be some constant less than 1. So alpha kind of determines that if alpha is larger than 1, your condition number will start to compound. So the error in the previous computation actually like compounds, multiplies with the next computation. And in fact, you will end up getting something like n to the power d as your, where d is the depth, as your condition number. So alpha just, so it doesn't go into the condition number.
What is d?
Yeah, d is the depth. So d is like the number of number of edges in the graph. So here it would be n minus 1, right? So it's actually an exponential quantity if alpha is larger than 1.
Okay, other questions?
You've assumed that the graphs are bow-free for all of the results, right?
Yeah.
So how do people overcome this assumption? I mean, if you want to do identifiability.
So yeah, so bow-free assumptions are like kind of not a good, not a very general assumption. So which is why people try to like get more results which don't depend on bow-free, but how do they overcome it? So I guess there are two kind of questions. How do they overcome it in theory versus practice? In practice, it's like I would say these are all still very far from practice. So in that sense, I don't have a good answer there. Yeah, so in theory, like you kind of like the starting point is still trying to solve this set of equations, which
I see. Okay.
Yeah, they still want to solve this set of equations, and they just try to identify like what kind of graphs can you solve this. So if you like stare at it a bit more here, it's not that like, so bow-free is a very loose sufficient condition to solve this set of equations. In fact, like you can get much more better coarser conditions, but again, this is only a sufficient condition, so that is the problem. So here you're throwing away all the.
Sorry, there are no necessary conditions known. There are known, right, for identifiability.
So when you mean necessary, you mean that. So you know some set of necessary conditions, you know some set of sufficient conditions, but they don't encompass all set of graphs essentially. Meaning there are some family of graphs where you don't know whether it's one way or the other.
Okay, nice. Okay, thanks.
So yeah, I think like there are a whole bunch of open questions. Like one of the probably the most important question is that identifying precisely characterizing the set of graph for which generic identifiability is known. And of course, like improving these conditions for more specialized versions. For instance, I think as Arnab said, like, can you get rid of these kind of this condition here if it's if the noise is a bit more structured, if it's random, or if it's coming from some other known dynamics, instead of assuming the worst case bounds. And I'm fairly confident that you will have you can get rid of such conditions if you assume such things.
Another question, I'm not sure if it makes sense, but I mean, like,
right?
So in practice, do people actually use this algorithm for finding the coefficients, or is something else used?
Yes, so I think I would say, like, there are like I mean, you kind of have to define what practice means, but
Yeah.
my assumption, just looking at all these papers and even us trying to run experiments, is that it's still very far from practice. So the one of the thing that kind of bottlenecks the practice aspect of this is the fact that you have to start with a model, and there's usually disagreement on should you start with a model and is this the right model. So
because, I mean, I would think, I mean, like, yeah, I mean, like, can't you do it like by node regression or something like that? I mean, like, where you at each node you
yeah, so you do a
linearly.
right, exactly. So that's kind of like the way people try to build these models. So that you just take every pair, do a regression, use that to see whether these two are related or not, and so on. Except that, like, the problem with even doing that is that doesn't account for these bidirected edges. So yeah, so there are like a lot of limiting factors here. So the fact is, getting the model is a pretty hard task, and unless you have very deep domain knowledge, I mean, even then, the domain knowledge usually only lets you get the directed edges. The bidirected edges require like it's non-trivial to identify it even in any single domain. Outside of that, yeah, it's unclear to me, like, how much this is used in practice at this point. So it's at this point, I think it's primarily just a fun mathematical question, if I had to characterize it.
I guess you guys should also look into the sigma inverse thing, because it seems to me like, so from what I understand, like, when people define Gaussian graphical models also, so initially people looked at sigma, but in some sense sigma inverse makes a little more sense, because you are I mean, so like, if you have two variables which are conditionally independent given the third, then basically the non-zero I mean, the non-zero edges given by the inverse of the covariance matrix exactly gives that Markov structure, meaning, like, if you remove that, so if A and B are supposed to be independent condition on C, then if you remove C in the graph, then A and B become disconnected.
I see. So yeah, I think that's a good point.
So I think it makes more sense for that inverse matrix to be sparse than saying that the sigma matrix itself is sparse.
Right. That's a good. So you mean omega, right?
Sorry, omega. Yeah.
Right. Yeah, I think that's a good point. So we should definitely look at it and see if that like how these two assumptions trade off with each other.
The sparsity somehow doesn't play a role for you, right? I mean, like,
yeah, we don't use sparsity at all, but sparsity could definitely help us, like in some sense, especially for a random matrices result. Like, sparsity definitely helps us. So if zero patterns of omega inverse is known, it will definitely help us. Yeah. So yeah, thanks for that. We'll look into it.
Sure.
Yeah.
Any other questions? Okay, thank you, Karthik. That was a wonderful talk.
Yeah.
I think we
Yeah,
got a
thanks.
lot out of it. Thanks.
Yeah, thanks a lot.
Okay, bye. So is it okay if I put the recording on the YouTube channel?
Yeah, sure. That should be okay.
Okay, great.
Yeah,
Thank you.
thanks. And
Bye.
is this the Zoom link for the next talks as well? I mean, if
No, it's not, but I can put you on the mailing list.
Yeah, that'll be good.
So that
If
you
you
can
can
get
do that.
announcements.
Yeah. Yeah, thanks.
Great. Thank you.
Yeah.
Bye.
See ya.